Hi, today we're talking about verifying trigonometric identities. We see here reciprocal and ratio identities, and we see that secant theta is 1 over cosine theta, for example, and cosine theta is 1 over secant. Well, we can take either one of these identities and write them in the reverse order. You see 1 over cosine can equal secant, and 1 over secant equals cosine. These identities are the same, they're just written in the reverse order. And here we see that tangent is sine over cosine, but if we see sine over cosine theta in an expression, we can write it as tangent theta. Now here are the Pythagorean identities. These are very familiar to you. And the second one here, cosine squared, is 1 minus sine squared theta. But if we see in an expression 1 minus sine squared theta, we can rewrite it as cosine squared theta. Likewise, if we see secant squared theta minus 1 in an expression, we can rewrite it as simply tangent squared theta. We're going to be using these identities throughout this discussion. So an identity that we've seen is an equation, and the equation is true for all possible argument values. Now we're familiar with the Pythagorean identity, cosine squared plus sine squared equals 1, and let's show that that's true when theta is equal to pi over 6. We put pi over 6 into theta, and we see cosine squared of pi over 6 plus sine squared of pi over 6 equals 1. And we put a question mark to say, well, is it equal to 1? I sure hope so. Of course, cosine squared of something means really cosine of that value, quantity squared. And the same is true for sine. So sine of pi over 6 quantity squared. Then we evaluate what's inside. Cosine of pi over 6 is square root of 3 over 2, and it's being squared. And then sine of pi over 6 is 1/2, and it's being squared. And when we square these fractions, we get 3/4 plus 1/4. That's 4/4. Of course, that equals 1. So that is a true statement. And that's how identities are. They are true for any value we pick for theta. Now, when we verify identities, it's set up like an equation, but we do not treat it like an equation, meaning we do not solve an identity, a supposed identity, one that we're trying to verify or prove. Instead, what we do is manipulate only one side of the expression, and we make it look exactly like the other side. And once we do that, well, then it's been verified. Now, if an identity has actually been verified, like our Pythagorean identities or ratio identities or reciprocal identities, then we can write alternative identities based on the rules of equations. For example, because secant theta is 1 over cosine theta, we already know that's true, we can treat it like an equation and multiply each side by cosine theta. What that does is gives us cosine theta times secant theta equals 1, basically a new identity. I mean, it's not really new, but it's a new form of the same identity. Or, as we've seen in the past, we can take a Pythagorean identity and, in this case, subtract cosine squared from each side and generate a new form of that identity. In this case, sine squared theta equals 1 minus cosine squared theta. Or, as we've seen earlier, we can divide each side of that equation by cosine squared. And what that does is create two fractions on the left, each divided by cosine squared, and the fraction on the right, 1 over cosine squared theta. But what we get from that is a new looking identity. 1 plus tangent squared theta equals secant squared theta. It's really not a new identity, it's just a different form of what we already know. So let's go ahead and practice verifying these identities. We'll start with secant x over tangent x equals cosecant x. Now let's convert everything to sine and cosine on the left side only. Secant is, of course, 1 over cosine, and tangent is sine over cosine. When we have a fraction divided by a fraction, we're going to write the top fraction, 1 over cosine x, times the reciprocal of the bottom fraction, in this case cosine over sine. cosines divide out, we just get 1 over sine x, which is cosecant x. Well, that's exactly what we want it to be, which is the same as on the right. Notice that we didn't write an equation all the way down. We just waited to show it at the very end that the left side and right side are indeed identical. And so we verified that identity. Here we actually have the same identity to verify. We're going to use a different technique. Instead of first writing everything in terms of sine and cosine, we're going to split the fraction on the left side into secant times 1 over tangent x. Then we can use a reciprocal identity because 1 over tangent x is cotangent x. And then we have secant times cotangent. Now we can convert to sine and cosine. 1 over cosine times cosine over sine. The sines divide out. We get the same result as we got earlier when we did it the first time. 1 over sine x becomes cosecant x, and that equals cosecant x. Now, every time I personally finish a verifying or proof, I write QED, which stands for Quod Erat Demonstrandum. That's Latin. It means that which we wanted to demonstrate, or something like that. QED. You don't have to write that. I write it. I can't help myself. Okay, so here's a new identity to prove anyway. And this time we're going to write everything in terms of sine and cosine. Well, first of all, let's put down the actual identity. It's sine x over cosecant x plus cosine x over secant x equals 1. So converting to sine and cosine, we have sine over the cosecant. Cosecant is 1 over sine plus the cosine is as it is, but the secant becomes 1 over cosine x. Now on the left side, the far left fraction, we're going to write the numerator as sine x over 1, and then times the reciprocal of the denominator, also sine x over 1. Likewise for the second fraction, numerator is cosine x over 1 times the reciprocal of the denominator, also cosine x over 1. That gives us sine squared x plus cosine squared x. And by a Pythagorean identity, that's equal to 1. 1 equals 1, QED. Here's that very same identity to verify. We're going to use that second technique this time, where we separate the fractions so that the sine x over cosecant becomes sine x over 1 times 1 over cosecant. And cosine over secant becomes cosine over 1 times 1 over secant. You don't have to do it this way. I just like to show you this option. Of course, sine x over 1 is sine x, but 1 over cosecant x is also sine x, plus cosine x times, well, 1 over secant x is also cosine x. Again, we get sine squared x plus cosine squared x, and we know that that equals 1 because that's the Pythagorean identity. QED. Let's rewrite this identity that we're supposed to prove. Tangent x plus cosine x is equal to sine x times quantity secant x plus cotangent x. This time, we're actually going to manipulate the right side because that seems to be a little bit more complex. We're going to distribute sine x to get sine x times secant x plus sine x times cotangent x. Then we'll convert to sine and cosine where we can. Let's see, sine x times secant is 1 over cosine, plus sine x times cotangent is cosine over sine. And I'll put each sine over 1 to kind of make it multiply fraction by fraction. Sometimes we can't see where it is that we're going, but if we look at where we're headed, we want to end up getting tangent x plus cosine x. And you can start to see that developing on the right side. Sine x times 1 over cosine x becomes sine over cosine. And the second fraction, well, the sines are going to cancel to give us the cosine that we need. So sine over cosine plus cosine becomes tangent x plus cosine x. Again, we did not write the left-hand side down all the way until the end. And so we've verified this identity, QED. And here's another example. Tangent x times cosine x plus cosecant x times sine squared x. And what it is to equal is 2 sine x. We'll clearly work on the left side. It's much more complicated. So tangent x is sine over cosine, and cosine is just cosine over 1. Cosecant x is 1 over sine x, and sine squared x doesn't need to change. Maybe put it over 1, sure. The first pair of fractions, we can divide out cosine x, we see, and we get sine x plus, let's see, in the second pair of fractions, we can divide out sine x, and we're left with sine x all by itself. So what we have here is sine x plus sine x, that's 2 sine x, and that's exactly what we want to get. QED. For our next example, we're going to need to get common denominators. That happens when one of the fractions has a denominator and another one doesn't, but we need to add them together or maybe subtract. Then we have to have common denominators. So this is sine x plus cotangent x times cosine x equals cosecant. We'll write sine x plus, the cotangent x is cosine over sine, times cosine, and I'll make that over 1. So our next line is sine x plus cosine squared x over sine x. And this is where we need to get common denominators. The first fraction does not have a denominator except of 1, and yet we need a denominator of sine x before we can combine these together. So we multiply by sine x over sine x on the first fraction, and that gives us sine squared x over sine x. Now notice that we're combining the numerators to get that common denominator. We created a common denominator of sine x, allowing us to do that. And that numerator, sine squared plus cosine squared, is 1. 1 over sine x. Oh, I guess I've run out of room, so 1 over sine x is cosecant x, and that's what we want to get. Cosecant x, so QED. In this example, we have tangent x plus cotangent x equals secant x times cosecant x. It's hard to know which side to start, but I guess we'll start on the left with the addition. So tangent is sine over cosine, and cotangent is cosine over sine. Now in this case, the common denominator is cosine x times sine x. So we'll multiply the first fraction by sine over sine, and the second fraction will multiply by cosine x over cosine x. Let's see what that gives us. That'll be sine squared x over cosine x times sine x plus cosine squared x over sine x times cosine x. And I can see the common denominator. Now you might look at that and say, well, oh, we have sine squared plus cosine squared. Can we make that 1 right away? And the answer is no, we can't make that 1 because they're actually in 2 separate fractions. We have to combine the fraction and get that expression as we see right now, sine squared x plus cosine squared x all together. And then in the next step, we can write it as 1. So 1 over cosine x times sine x. Sometimes we get to a place in our proof where we're not exactly sure where to go. So it can be helpful sometimes to look at what the answer is supposed to be and kind of simplify that and see, what happens here. Well, in this particular case, secant is 1 over cosine, and cosecant is 1 over sine, which, when we multiply those, can combine to a single fraction. But what that actually allows us to do is kind of see where we should go in reverse. It gives us a guide as to how to get to the final answer, secant x times cosecant x. And that happens by splitting the fraction up into 1 over cosine x times 1 over sine x. Then we have the secant x times cosecant x, which is what we want, QED. Now let me just remark that this stuff we did off to the side in green is scratch work. It's not actually part of the proof officially. It just gives us some guideline as to how we should proceed with the proof. Okay, let's talk about conjugates and the difference of squares. First, a quick reminder of what conjugates are. Conjugates always come in pairs, such as A plus B and A minus B. And the thing about conjugates is the first terms are exactly the same, A and A, and the second terms are opposites, B and negative B, such as x plus 3 and x minus 3. And the connection between conjugates and the difference of squares is, if we start with the difference of squares, such as x squared minus 9, it always factors into a pair of conjugates, x plus 3 times x minus 3. Likewise, if we have a pair of conjugates that we multiply, they always multiply to become the difference of squares. X plus 3 times x minus 3 is x squared minus 9. Oh, one more thing before we continue. We'll often see squares either on the left side or the right side of the expression, or maybe both. And if we ever see a square, it's likely that one of the Pythagorean identities will be used. It doesn't have to be, but it's likely that it will. We'll see that in example G here. X to the fourth x minus sine to the fourth x over cosine squared x equals 1 minus tangent squared x. A lot of squares. The numerator, interestingly enough, is a difference of squares. I know it's to the fourth power, but it's actually cosine squared x plus sine squared x, that's one conjugate, times cosine squared x minus sine squared x. And it's all divided by cosine squared x. Now where we see the Pythagorean theorem is in that first conjugate, the cosine squared x plus sine squared x. That equals 1. And we can use that immediately. It gets eliminated, and we get just cosine squared x minus sine squared x over cosine squared x. Now that numerator is not a Pythagorean identity. But take a look at where we're trying to get. We want to get to 1 minus tangent squared x. And that denominator of cosine squared, notice that it actually belongs to both terms in the numerator. So we can split the fractions up into cosine squared x over cosine squared x minus sine squared x over cosine squared x. And when we simplify each of them, we get 1 minus tangent squared x. And that's what we want to get. QED. Let's see what's next. Okay, in this example, 1 plus cosine theta equals sine squared theta over 1 minus cosine theta. The only square here that we see is the sine squared theta. And there is a Pythagorean identity for it, 1 minus cosine squared theta. And it's divided by 1 minus cosine theta. Well, that numerator has turned into the difference of squares, so we can factor it into 1 plus cosine theta times 1 minus cosine theta. And it's all divided by 1 minus cosine theta. And you might notice that in the numerator and denominator now, yes, we have that common factor of 1 minus cosine theta, and it divides out. And notice what we're left with, just 1 plus cosine theta, and that's what we're looking for. QED. Here is that same identity to verify. 1 plus cosine theta equals sine squared theta over 1 minus cosine theta. This time we're going to take a different approach. This time we're going to multiply the denominator by its conjugate, 1 plus cosine theta. And of course that means multiply both top and bottom, numerator and denominator. So we're really multiplying by 1. Now this does a couple things for us. One is it is conjugates in the denominator, and of course they multiply to get difference of squares. 1 minus cosine squared theta, which turns into sine squared theta. The other is we've introduced 1 plus cosine theta into the right side, which is exactly what we want. So let's see where this goes. Notice sine squared theta times the quantity 1 plus cosine theta. I'm not going to distribute this time because we know that the sine squares are going to cancel out eventually. And we already have the 1 plus cosine theta. We don't want to get rid of it. In the denominator, we do get the difference of squares, 1 minus cosine squared theta. That's the Pythagorean identity. Becomes sine squared theta in the denominator. And those divide out. And lo and behold, 1 plus cosine theta on the right equals 1 plus cosine theta on the left. Dare I say it? QED. All right, let's see what's next. In this one, we don't have anything squared. Well, let's see what happens. 1 plus sine x over cosine x equals cosine x over 1 minus sine x. We just discovered a way that we can introduce squares into an expression, and yes, that's to multiply by the conjugates. In this case, we're going to multiply by 1 plus sine x, the conjugate of the right side denominator. And as we do, we've introduced the 1 plus sine x numerator on the left side, so at least we're heading in the right direction. What we get is cosine x times the quantity 1 plus sine x, all over the denominator, which is the difference of squares now, 1 minus sine squared x. And that's Pythagorean. So the numerator is cosine x times 1 plus sine x, all over cosine squared x. Now we can divide out cosine x from the numerator and denominator. And we now have exactly what we're supposed to have on the right side. 1 plus sine x over cosine x. That's what we're supposed to get. 1 plus sine x over cosine x. QED. All right. Well, we're going to do something a bit different this time. We're going to see now some non-identity equations. And if these equations are not identities, well, that means that they're not necessarily equal to each other, left side and right side. We can see here that this equation is actually true for some values of x, but it's not true for many other values of x. So that means it's not an identity. What we're going to do is put a value in x equals pi to actually demonstrate that the left side and the right side are not the same. If they're not the same, then this can't be an identity. So that's the sine of pi minus cosine pi, quantity squared, and it equals, or we want to find out if it equals, sine squared pi minus cosine squared pi. We're going to evaluate each part of this. Sine of pi is 0, minus cosine pi is -1, and that's a whole quantity being squared. And on the right, though, the individual pieces are squared. Sine pi is being squared, 0 squared, minus -1 quantity squared. So on the left, 0 minus -1 is 0 plus 1, which becomes 1 quantity squared. On the right side, 0 squared, of course, 0 minus 1. The left side is +1, the right side is -1, and they're not equal. Of course, that's false. So what that shows us is the equation is not an identity. Now, something interesting about that is we found at least one value that makes it not work, and that's called a counterexample. And there are actually many others. There are lots of counterexamples that we could have found here. Pi was simply an easy one. We could have found x is pi over 6, x is -pi over 3. So now our task is to find a counterexample to demonstrate that this equation is not an identity. So let's try x equals 0. This becomes cosine of 2 times 0 equals 2 times cosine of 0. We first evaluate inside the parentheses. Cosine of 2 times 0 means cosine 0. And on the right side, 2 times cosine 0, well, cosine 0 is 1. In fact, that's what we get on the left side as well. 1 equals 2 times 1 is 2. That's clearly false. So again, this equation is not an identity. Our counterexample that we chose was x equals 0. That's one counterexample. There are many, many others. Here's another example. Sine theta plus cosine theta equals 1. Now you might look at that and say, oh, that's Pythagorean. Well, it's not, because nothing's being squared. So let's try theta equals 0. Sine of 0 plus cosine 0 equals 1, question mark, or does it? Sine of 0 is 0, cosine 0 is 1, 0 plus 1, oh, actually they are equal. Oh, so does that mean that this is an identity? Well, it's true, but it's true for that one value. That doesn't mean it's true for every value. And to be an identity, it would have to be true for every value. So let's see if there's another counterexample that we can try. Let's do 180 degrees. So sine of 180 degrees plus cosine of 180 degrees, is that equal to 1? Sine of 180 is 0, but cosine of 180 is negative 1, and you notice nothing's being squared here. And 0 plus negative 1, of course, is negative 1. So to say negative 1 equals 1, well, that's clearly false. So we did find a counterexample. And again, the equation is not an identity. The counterexample is 180 degrees. We could have used many, many other counterexamples. Well, I hope this has been helpful to you. A lot going on in this video. Until next time, take care.